So welcome. In this video we shall discuss the linear regression estimator. So in my previous video I have discussed the difference estimator for estimating the finite population mean, which is given by yd bar equal to y bar minus beta into small x bar minus capital X bar, and we have seen that this estimator is optimum. That means it will attain the minimum variance when we use beta yx in place of beta. That is the population regression coefficient of y on x. So sample regression estimator is a particular case of the difference estimator when we use the least square estimate of the population regression coefficient of beta yx in place of this beta 0. That means we use beta cap, that is equal to syx by sx square that is equal to b. So the linear regression estimator for estimating the finite population mean is given by YLR bar, that is equal to y bar minus beta cap into small x bar minus capital X bar, that is equal to small y bar minus b small x bar minus capital X bar, where b equal to the beta cap, that is equal to syx by sx square. This is the sample regression coefficient of y and x. Now to find the bias and variance of this estimator, we have the linear regression estimator, that is equal to y bar minus beta cap into small x bar minus capital X bar. So expectation of y LR bar equal to expectation of y bar minus expectation of beta cap into small x bar minus capital X bar. So that is equal to y bar minus expectation of beta cap small x bar minus expectation of beta cap capital X bar. So that is equal to y bar minus expectation of beta cap small x bar minus expectation of beta cap into expectation of small x bar, because expectation of small x bar equal to capital X bar. So y bar minus, this is covariance of beta cap x bar, expectation of y LR bar minus y bar equal to minus covariance of beta cap x bar. So this is bias of y LR bar equal to minus covariance of beta cap x bar. So this is the bias of the regression estimator. So this covariance becomes 0 if the relation between x and y is linear. So if x and y is linearly related, then the linear regression estimator, this YLR bar, is an unbiased estimator for the population mean y bar. Now we have to find the approximation for the bias. Now we have the linear regression estimator YLR bar equal to y bar minus beta cap small x bar minus capital X bar, where beta cap equal to b, that is equal to small syx by small sx square. So this is beta cap is the sample regression coefficient of y on x. So as usual, so we have to use Now put small y bar equal to capital Y bar plus epsilon 1, small x bar equal to capital X bar plus epsilon 2, small sx square equal to capital Sx square plus epsilon 3, small syx equal to capital Syx plus epsilon 4, where expectation of epsilon I equal to 0 or I equal to 1, 2, 3, 4. Now variance of y bar equal to expectation of epsilon 1 square. Similarly, variance of x bar equal to expectation of epsilon 2 square. Variance of sx square equal to expectation of epsilon 3 square, and variance of syx equal to expectation of epsilon 4 square. So now the linear regression estimator can be written as this is y bar plus epsilon 1 minus syx plus epsilon 4 by sx square plus epsilon 3 into epsilon 2. So that is equal to y bar plus epsilon 1 minus syx, taking common 1 plus epsilon 4 by syx divided by sx square 1 plus epsilon 3 by sx square into epsilon 2. So that implies y LR bar minus y bar equal to epsilon 1 minus syx by sx square. This is population regression coefficient beta, so this will be 1 plus epsilon 4 by syx into 1 plus epsilon 3 by sx square. This is inverse into epsilon 2. Now since epsilon 3 by sx square mod less than 1, so we can expand this 1 plus epsilon 3 by sx square inverse. So we get the linear regression estimator minus y bar, that is equal to epsilon 1 minus beta epsilon 2 1 plus epsilon 4 by syx into 1 minus epsilon 3 by sx square plus epsilon 3 square by sx 4 minus up to so on. So this will be equal to epsilon 1 minus beta epsilon 2 1 plus epsilon 4 by syx minus epsilon 3 by sx square plus epsilon 3 square by sx to the power 4 minus epsilon 4 epsilon 3 by syx into sx square plus epsilon 4 epsilon 3 square by syx sx to the power 4 up to so on. Now this is approximately equal to epsilon 1 minus beta epsilon 2 into 1 minus epsilon 3 by sx square plus epsilon 4 by syx plus order of epsilon to the power 3. So this is approximately equal to epsilon 1 minus beta epsilon 2 plus order of epsilon square. So Now neglecting order of epsilon square, we get YLR bar minus Y bar equal to epsilon 1 minus beta epsilon 2. So this implies expectation of YLR bar minus Y bar equal to 0. So that is the linear regression estimator YLR bar is an unbiased estimator of Y bar up to order of epsilon square only. Now neglecting the epsilons of order 2, we get YLR bar is an unbiased estimator of the Y bar. Hence YLR bar minus Y bar equal to epsilon 1 minus beta epsilon 2, that is equal to Y bar minus Y bar, this is epsilon 1 minus beta, this is small x bar minus capital X bar. So that implies YLR bar equal to small y bar plus beta y bar minus beta small x bar minus capital X bar. So this is our linear regression estimator. So now let this be equation 1. So we have already the linear regression estimator YLR bar equal to Y bar minus beta cap into small x bar minus capital X bar. So now from this equation and this equation, we have seen this is approximately equal to up to order of epsilon square. We have seen that if we use beta in place of beta cap here, the linear regression estimator is unbiased. The sample regression coefficient beta cap equal to the population regression coefficient beta of y and x, we have the linear regression estimator YLR bar is an unbiased estimator of the y bar. So now the large sample variance of the linear regression estimator, that is equal to expectation of epsilon 1 minus beta epsilon 2 whole square. So that is equal to expectation of epsilon 1 square plus beta square epsilon 2 square minus 2 beta epsilon 1 epsilon 2. So this is expectation of epsilon 1 square, that is variance of y bar, plus beta square, this is variance of x bar, minus 2 beta covariance of x bar y bar. So now this is equal to 1 by small n minus 1 by capital N, this is sy square plus beta square sx square minus 2 beta syx. Now but beta is the population regression of coefficient of y and x, so beta equal to syx by sx square. So using this will be 1 by small n minus 1 by capital N, this will be sy square plus beta square sx square, this will be syx square by sx to the power 4 into sx square minus 2 beta, this will be syx by sx square into syx. So this will be 1 by small n minus 1 by capital N, this is sy square minus 2 syx square by sx square. So we have have rho is the population correlation coefficient between y and x, rho equal to syx by sy into sx. So rho square will be syx square by sy square sx square. So this implies rho square sy square equal to syx square by sx square. So using this value here we get this is equal to 1 by small n minus 1 by capital N sy square minus rho square sy square. So this will be equal to 1 by small n minus 1 by capital N sy square 1 minus rho square, which is the variance of the difference estimator in its optimum case. So now if you neglect the terms of up to order of epsilon to the power 3 or writing up to order of epsilon square, we get the linear regression estimator minus y bar, that is equal to epsilon 1 minus beta epsilon 2 equal into 1 minus epsilon 3 by sx square plus epsilon 4 by syx. This we have already derived that. So this is now equal to epsilon 1 minus beta epsilon 2 plus beta epsilon 2 epsilon 3 by sx square minus beta epsilon 2 epsilon 4 by syx. So now expectation of YLR bar minus y bar, that is equal to expectation of epsilon 1 minus beta epsilon 2 plus beta into expectation of epsilon 2 epsilon 3 by sx square minus beta expectation of epsilon 2 epsilon 4 by syx. Now this is equal to this expectation, this becomes 0, so this will be beta expectation of epsilon 2 epsilon 3, this is covariance between small x bar and small sx square by capital Sx square minus beta covariance between this x bar and syx by syx. Since expectation of this is 0, so now we have covariance between x bar and syx equal to n into n minus n divided by n minus 1 n minus 2 mu 2 1 by n into 1 by syx. Similarly, covariance between x bar and sx square, this is equal to n into n minus n by n minus 1 into n minus 2 mu 30 by n into 1 by sx square. So where mu rs is the rth order bivariate moment, that is equal to 1 by n summation I equal to 1 to n xi minus x bar to the power r yi minus y bar to the power s. So So now n minus 1 into Sx square, that will be n into mu 20, and n minus 1 Syx, that will be n into mu 11. So using these values we can get the covariance, the bias in the linear regression estimator equal to expectation of YLR bar minus Y bar, that is equal to n minus n by n minus 2 into beta by n mu 30 by mu 20 minus mu 21 by mu 1. So this is the approximate bias of the linear regression estimator if we return the terms up to order of epsilon to the power 3. Now we have obtained the bias and variance of the linear regression estimator. Now we have to find the estimator of the variance of the linear regression estimator, rather consistent estimator for variance of YLR bar. Now we have seen that the variance of YLR bar, that is equal to 1 by small n minus 1 by capital N Sy square into 1 minus rho square, where rho is the population correlation coefficient between y and x. So that is equal to 1 by n minus 1 by capital N, this is Sy square plus beta square Sx square minus 2 beta Syx. This we have already derived, where beta is the population regression coefficient of y on x. Now using this is equal to 1 by small n minus 1 by capital N. This will be summation I equal to 1 to n. This will be yi minus y bar minus beta xi minus x bar whole square divided by n minus 1. So a consistent estimator of variance of linear regression estimator is given by 1 by small n minus 1 by capital N summation I equal to 1 to small n. This will be small yi minus small y bar minus beta cap xi minus x bar whole square by n minus 2. So here we have written n minus 2 because we are estimating two constants, one is alpha, another is the beta, the regression estimator. In the regression estimator, as y equal to alpha plus beta x, so it will lose 2 degrees of freedom. Now we shall compare the regression estimator with other estimators, and the simple mean estimator we shall compare. So the regression estimator YLR bar is more efficient than the simple mean estimator y bar if variance of y bar minus variance of YLR bar is greater than 0. So linear regression estimator will be more efficient. So that means 1 by small n minus 1 by capital N sy square minus, this is variance of the simple mean estimator, and variance of linear regression estimator, this will be 1 by small n minus 1 by capital N sy square 1 minus rho square, this is greater than 0. So that implies 1 by small n minus 1 by capital N sy square into rho square, this is greater than 0. Now this is always true. So the regression estimator YLR bar is unconditionally superior to this. Now but it sometimes what happens, we can, our linear regression estimator YLR bar, that is equal to y bar minus beta cap small x bar minus capital X bar. So if for some data it may happens that the magnitude of this exceeds the value of y bar, so in that case this becomes negative, but y bar it is positive. So in that case the linear regression estimator may not be admissible because of its negative values. So now we shall compare the linear regression estimator with the ratio estimator YR bar. The comparison between the regression estimator and the ratio estimator. Now our linear regression estimator will be more efficient than the usual ratio estimator if variance of the ratio estimator minus variance of the linear regression estimator, that is greater than 0. So that implies a ratio estimator, we have the variance 1 by small n minus 1 by capital N sy square plus r square sx square minus 2r rho sy sx minus 1 by small n minus 1 by capital N sy square 1 minus rho square, this is greater than 0. So that implies 1 by small n minus 1 by capital N, this is rho square sy square minus plus r square sx square plus minus 2r rho sy sx, this is greater than 0. So that implies 1 by small n minus 1 by capital N r sx minus rho sy whole square greater than 0. So this is always true, because this is positive, this is also positive. So the linear regression estimator is always more efficient than the ratio estimator, and both becomes equally precise or equally efficient is if this term equal to 0. That means rsx equal to rho sy, that implies r equal to rho sy by sx, that is equal to beta yx or beta. So that implies when r is equal to beta, then the linear regression estimator and the ratio estimator are equally efficient. So that is r equal to beta means that the relation between y and x is linear, and the regression equation of y and x passes through origin. So that means in simple, the relation between x and y is linear passing through origin. Thank you.